Okay, so here we are for the last module of the week, calculating length. And so this is following on from calculating area, which followed on from Riemann sums. So at first you might not think that length is a good candidate for a Riemann sum. However, length is like area in that it's additive, right? So if you've got 5 different lengths, the total length is just adding up the 5 lengths together. But the problem is, how do we think of it as a product? Because remember, that's what we need for a Riemann sum. Well, let's look at the simplest example, that of just a straight line. So let's say it has a slope m. So delta y equals m times delta x. Okay, and you see the right angle triangle there. It has a hypotenuse. So by Pythagoras, the length of the hypotenuse is square root of delta x squared plus delta y squared. But because it's a straight line, we can replace delta y by m times delta x. And so we get delta x squared plus m delta x all squared. So we can pull out a delta x squared. And if we pull it out of the square root, it becomes just delta x by itself. So it's square root of 1 plus m squared times delta x. So this is the product that we need. And again, it kind of follows that we can sum up things. Okay. So for example, if you go for a step of 2 at a slope of 3 and a step of 1 at a slope of 4, okay, so delta x is 2, going at a slope of 3, so that's going to be 2 times square root of 10. And then you go in a slope of 4, so that's 1. You're doing a step of 1 times the square root of 17. And that means that altogether you've traveled in your dogleg little trip around 10.45. So the module question is, if you go along in the x direction for a step of 4 at a slope of 3/4, how far have we traveled? Okay, and the answer should be greater than 4. Okay. So the trickier problem then is, we've seen this before, what happens if we travel along and our slope just keeps changing? Well, that's when the Riemann sum comes in. So estimating length. So our function curves along on some interval, and so we take our interval and we break it up into subintervals, delta x1 through to delta xn. And the idea is, since we've made pretty small subinterval, the function looks kind of straight on that subinterval. So we can approximate it as a straight line with the slope of the derivative of the function. So our approximation, so remember we're sampling at a point on that subinterval. So our approximation is of the length then is the sum of square root of 1 plus the derivative squared times delta x, the length of the subintervals. So this gives us a Riemann sum, not of the function f, but of some other function g, which is the square root of 1 plus the derivative squared. Okay, so let's look at some examples. So let's look at the one prime example we know, of course, is the circle. And so if you think of it, pi gives you both an area and a length. How can that be? Well, let's do a quarter circle of radius 1. That also has length pi on 2, right? Because the whole circle has radius, circumference 2 pi. So if we just take a quarter circle, that's going to be pi on 2, which is around 1.57. So I'm using 4 equal subintervals. I'm sampling at the midpoints. So since my intervals are 0 to a quarter, quarter to a half, half to 3/4, 3/4 to a half, my sampling points are an 1/8, 3/8, 5/8, and 7/8. Now the formula for a semicircle is square root of 1 minus x squared. So to take the derivative of that, I do the chain rule. So I let u equal 1 minus x squared. So the derivative of that is minus 2x. And then the derivative of square root of u is a half 1 over square root of u. So I multiply those together. The 2 times a half cancels out. We've got a minus. So we've got a minus x on top. And we've got the square root of 1 minus x squared on the bottom. Okay, and so for our finding length function, then we take square root of 1 plus the derivative squared. That becomes square root of 1 plus x squared over 1 minus x squared. Put that over a common denominator, 1 minus x squared. So on top I get 1 minus x squared plus x squared. X squared's cancelled, so I'm just left with 1 divided by the square root of 1 minus x squared. Okay, and then to do our approximation, right, our interval goes from 0 to 1. We cut it into 4 equal parts, so it's 1/4 is the width, and then then I just plug in the values of the function at those different points, and I get around 1.358. And you notice it's much worse than what we did for area. For the area, we did a much better job. You kind of see, if you kind of look at it, especially the last little segment from 3/4 to 1, it seems to be a big error. So to get a better answer, we should use the Excel file Riemann.xls that I've shown you before. We're not going to do that. It actually turns out that this is very slow in giving you answers. Like for the area one, we saw pretty good approximation. This is much lower. Okay, so let's do a problem that we don't know the answer for. And so here's a graph of the function 0.4 times x to the 2.5. And we're going to do it on the interval 1, 3. Now, we can do a rough estimate, just look eyeballing it, because we can see it looks like it's a hypotenuse of a right triangle from 1 to 3. That's like a base of 2. And the height, it sort of goes from maybe a half to 6.5, so that's 6. So we expect the answer to be around square root of 40, 6.3. Okay, but let's actually figure what it is. So the derivative of that is down comes to 2.5. 2.5 times 0.4 is 1. That's why I use 0.4. And we subtract 1 from the power. So the derivative is x to the 1.5. So to estimate the length of this function on 1, 3, we do the Riemann sum of square root of 1 plus the derivative squared. I shouldn't call that fx. I should call it something else. Anyway, but that's just square root of 1 plus x cubed. But that's exactly the Riemann sum we did in the last module. And from there, we knew that so we know the answer there was around 6.23, which was the area under square root of 1 plus x cubed. So the area under square root of 1 plus x cubed is the same as the length of 0.4 times x to the 2.5. So it's kind of strange. It's just kind of like how pi is both a length and an area. This 6.23 is both a length and an area. Okay, and so that finishes up this module.